SemiMemes, a novel semi-supervised learning approach, is proposed for multimodal memes analysis, leveraging both image and text components to understand their underlying meanings and sentiments. This approach draws on insights from contrastive language image pre-training, a proven multimodal learning technique. By combining autoencoder and classification tasks, SemiMemes efficiently utilizes large amounts of unlabeled data available online. In this approach, the autoencoder task is used to learn representations of both image and text components, while the classification task is employed to predict the sentiment of memes. This combination enables the model to learn from unlabeled data and adapt to new, unseen data. The performance of SemiMemes is evaluated on two datasets: the Multimedia Automatic Misogyny Identification and Hateful Memes dataset. Results show that SemiMemes outperforms state-of-the-art multimodal semi-supervised and supervised learning models on both datasets. The proposed method has significant implications for social media platforms, as it can accurately analyze meme sentiments, thereby aiding in the censorship of harmful content. By leveraging the strengths of both image and text components, SemiMemes provides a more comprehensive understanding of memes, enabling more effective moderation of online content. The authors introduce a multimedia automatic misogyny identification dataset, showcasing examples of texts with corresponding labels. For instance, example A contains the text, "Me, my eternal love and affection, my perfect wife," with a label indicating it is not misogynous. In contrast, example B features the text, "So, if you're a feminist, how can you eat dairy?" with labels denoting it as misogynous, stereotypical, and objectifying. These examples highlight the complexity of identifying misogynous content, as the latter text contains a feminist identifier but perpetuates harmful stereotypes. Additionally, the authors draw from the Hateful Memes dataset, providing examples C and D. Example C contains the text, "When your ex asks you for help," with a label indicating it is not hateful. Conversely, example D features the text, "Don't decide the lineage given to you by your forefathers, do what's right, keep it white," with a label denoting it as hateful. These examples demonstrate the importance of nuanced classification systems to identify and distinguish between hateful and non-hateful content. These datasets and examples serve as a foundation for the author's proposed methodology, which aims to develop a robust and accurate system for automatic misogyny identification. By presenting these illustrative examples, the authors emphasize the need for a comprehensive understanding of the complexities and nuances involved in identifying misogynist content. The detection of harmful content in memes is a complex task, as it requires understanding both visual and textual aspects. Traditional natural language processing approaches are insufficient, as memes often rely on subtle cues and implied meanings. A multimodal approach that can effectively merge visual and textual features is necessary for sentiment analysis of memes. Manual labeling of memes is time-consuming and subjective, leading to disputes among human annotators. To address this challenge, a semi-supervised learning approach using multimodal data is proposed to simplify the annotation process. This approach leverages the strengths of both labeled and unlabeled data to enhance the performance of harmful content detection. The authors propose a multimodal semi-supervised learning approach, involving the development of a pre-trained model called Cross-Modality Auto-Encoder (CROMAE), based on contrastive language image pre-training (CLIP) features. This model can be trained on small datasets without labels. Additionally, a custom supervised model named RAWNCOOK is created, incorporating the extracted features of both CROMAE and CLIP. This approach utilizes knowledge from unlabeled data to improve the performance of the supervised model. Related works in multimodal content analysis typically rely on visual linguistic pre-trained models such as Visual BERT and CLIP. The CLIP model has shown impressive performance on large-scale datasets and has been used to develop the HateClip per architecture. This model achieved state-of-the-art performance on the Hateful Memes Challenge dataset, surpassing human performance. Previous approaches to meme sentiment analysis have also employed supervised learning based on Visual BERT or CLIP. However, semi-supervised learning approaches have been explored in various studies, including feature projection on an embedding space and cross-modal retrieval tasks. These approaches have shown promise in leveraging in-labeled data to improve the performance of multimodal models. The proposed approach aims to leverage the strengths of clip and semi-supervised learning to develop a robust model for detecting harmful content in memes. By utilizing the feature interaction between modalities and the knowledge from in-labeled data, the authors aim to improve the performance of meme sentiment analysis and address the challenges of manual labeling. Limitations and future work. The proposed approach relies on the availability of large-scale datasets and computational resources. Future work includes exploring the application of the proposed approach to other multimodal tasks and datasets. Researchers have explored various multimodal learning approaches, including semi-supervised learning, to develop their methodology. For example, Liang et al. Proposed an end-to-end model that simultaneously performs autoencoder and emotion classification tasks on visual, acoustic, and lexical signals from labeled and in-labeled videos. Gunti et al. Embedded images and words in the same space using a Siamese network, enabling the use of in-labeled meme data. Yang et al.'s comprehensive semi-supervised multimodal learning (CMML) method utilized in-labeled data to balance consistency and diversity among modalities, achieving competitive results on large-scale multimodal datasets. However, CMML's optimization is challenging due to its complex loss function and dependence on multilabel predictions. The author's methodology involves a two-stage process. In the first stage, an unsupervised pre-training phase is performed using the cross-modality autoencoder (CROMAE) model. This model predicts one modality's clip feature from the other modality's clip feature using only in-labeled data. The clip model's image and text encoders extract feature vectors from input image-text pairs, as illustrated in Figure 2. In the second stage, a new model is designed for learning the classification task on labeled data. The pre-trained encoders of CROMAE are frozen, and new representations, cooked features, are extracted from the original clip features. Both the cooked features and original clip features, raw features, are fused to predict the classification target, resulting in the raw and cooked features classification model, RAWNCOOK. The SemiMemes approach employs a two-stage architecture, as depicted in Figure 2. The first stage utilizes a cross-modality autoencoder (CROMAE) model, designed to leverage one modality to reconstruct the other modality. Two CROMAE models are employed: AE image and AE text. AE image takes clip features Phimage as input and predicts ftext as output, while AE text takes ftext as input and predicts Phimage as output. This is formally represented by equations 1 and 2, where Phimage and ftext denote the clip features of the image and text, respectively, and Phimage and ftext represent the estimations of AE text and AE image, respectively. Both autoencoders share the same underlying architecture, comprising a sequence of linear, PRELU, and linear layers, with all linear layers having identical dimensions of 768. The use of PRELU activation function, as opposed to the commonly used ReLU, enables the model to learn the negative values of the encoder's output. This design choice is motivated by the need to capture nuanced patterns in the data. The CROMAE models are trained to minimize the reconstruction loss between the input and output features, thereby enabling the learning of rich representations across modalities. This process allows the model to learn a shared latent space that captures the underlying structure of both image and text data. By doing so, the model can effectively leverage the strengths of each modality to improve the overall representation learning. In the realm of multimodal learning, the CROMAE model is specifically designed to capture the underlying distribution of each modality for semi-supervised learning. This model utilizes an encoder-decoder architecture with PRELU activation functions in both the encoder and decoder layers, as depicted in Figure 3. The CROMAE model consists of two separate models, one for images and another for text. Each model is trained using a mean square error loss function, with the objective of minimizing the difference between the reconstructed and original features of each modality. The loss functions for the image and text models are denoted as LAE image and LAE text, respectively, in equations 3 and 4. These functions measure the error between the reconstructed features, f, and the original features, f, of the image and text modalities. By training these models separately, the CROMAE captures the underlying distribution of each modality, which can be beneficial for semi-supervised learning tasks. In Stage 2, the RAWNCOOK classification model integrates both the learned latent representations from the CROMAE and the original clip features. This integration allows the model to leverage the strengths of both the raw and cooked features, enhancing its performance in multimodal classification tasks. In multimodal classification, a novel approach is proposed, combining the strengths of pre-trained models and autoencoders. Specifically, the encoder components of two pre-trained CROMAE models, eImage and eText, are utilized and frozen to preserve knowledge learned from large in-labeled datasets. The clip features, Phimage and ftext, are passed through their respective CROMAE encoders to obtain latent extracted features, Zimage and ztext. These features are then projected to 256 length vectors using a sequence of linear, ReLU, and dropout layers, and concatenated to form a 1024 length vector. This concatenated vector is fed into a final linear layer to learn the classification target. The author's intuition is that the latent features, Zimage and ztext, are informative due to their learning on large in-labeled datasets. However, they recognize that these features may not be powerful enough for classification on their own, as they were driven by different tasks. To address this, the authors propose fusing these, cooked, features with the original, raw, features outputted from clip, Phimage and ftext. This fusion approach aims to leverage the strengths of both feature sets. Notably, the authors highlight the importance of using PRELU in the CROMAE decoder, as opposed to ReLU, to learn negative values on Zimage and ztext, which would otherwise become noise in the classification model. The proposed RAWNCOOK model for classification is illustrated in Figure 4. Experimental results are presented using the Multimedia Automated Misogyny Identification (MAMI) dataset, which is the SEM-Eval 2022 Task 5 dataset. This dataset is designed to identify inappropriate memes towards women using both images and texts. The task consists of two subtasks. Subtask A binary classification problem that aims to classify memes with hateful content into two categories, misogyny and not misogyny, and subtask B, which involves identifying memes with misogynistic content. This study explores two multimodal hate speech detection tasks, MAMI and hateful memes, which present distinct challenges in identifying and classifying hateful content within memes. The MAMI dataset involves a multilabel classification problem with 4 binary labels: stereotyping, shame, protest, and violence. It consists of 10,000 memes for training, 1,000 for testing, and 2,000 validation samples from the training set. In contrast, the Hateful Memes Challenge, constructed by Facebook, is a binary classification task that detects hate speech in multimodal memes, with a dataset comprising 10,000 memes divided into development, test, and training sets. To preprocess the data in MAMI and SemiMemes datasets, the text undergoes a series of actions including URL removal, non-ASCII character removal, lowercasing, punctuation deletion, and resizing images to 224 by 224 dimensions. For the Hateful Memes dataset, only image resizing is applied to fit the input size of the clip encoder. To address the class imbalance in the MAMI dataset, the focal version of the distribution balanced loss, dB loss, is employed to optimize the multilabel classification problem. The focal dB loss is defined as LDB minus focal, xk, yk, equals -1, cn array summation I equals 0 rki, 1 minus p plus, gamma yki log, p plus 1 lambda p gamma minus, 1 minus yki, log, 1 minus p minus, where p minus equals 1 over 1 plus e minus lambda, zki minus nu I, and p plus equals 1 over 1 plus e minus, zki minus nu I, with nu I equals kappa b and b equals minus log 1 pi minus 1. This setup and loss function are used to evaluate the performance of multimodal hate speech detection models, such as SemiMemes and CMMLCLIP. The authors introduce the experimental setting and hyperparameters for their proposed method, SemiMemes, on the MAMI and hateful memes datasets. SemiMemes utilizes a rebalanced weight, RK, calculated using the negative probability, P-, positive probability, P+, logit of the model, ZKI, focusing parameter, gamma, scale factor, lambda, class-specific bias, nu-I, estimated bias variable, B, scale factor of B, kappa, and class prior probability, pi. The values of gamma, lambda, and kappa are set to 2, 5, and 0.1, respectively. For the hateful memes dataset, the authors use traditional binary cross-entropy, BCE, loss to optimize the binary classification task. The experimental setting involves randomly creating a labeled set and an unlabeled set for training from the original training set, with 3 scenarios featuring different proportions of labeled sets: 5%, 10%, and 30% of the original dataset. The atom optimizer is used with an initial learning rate of 1e4 and 0.25 for the initial value of alpha in the parametric ReLU (PRELU) activation. The learning rate is reduced after each epoch using the step LR scheduler with scenario-dependent gamma scheduler values, as shown in Table 1. The number of pre-training epochs, fine-tuning epochs, and batch size are set to 200, 200, and 40, respectively. For Stage 1 on MAMI, L2 regularization with a weight decay of 1e4 is employed. The model is trained on an NVIDIA RTX 6000. The authors compare SemiMemes with several baselines, including state-of-the-art methods for multimodal semi-supervised learning and multimodal supervised learning, such as CMMLCLIP and TIBVA. The experimental setting and hyperparameter choices are designed to evaluate the effectiveness of SemiMemes on the MAMI and hateful memes datasets, and to compare its performance with SOTA methods. The use of different scenarios and hyperparameters allows for a comprehensive evaluation of the method's robustness and adaptability. This comparative analysis evaluates the performance of SemiMemes on 2 benchmark datasets, MAMI and hateful memes, across various label settings. The model is pitted against state-of-the-art models, including CMMLCLIP, TIBVA, and HateClip-Per. On the MAMI benchmark, SemiMemes consistently outperforms CMMLCLIP and TIBVA across all label settings, achieving superior performance in both validation and test sets. The weighted average F1 measure scores for SemiMemes surpass those of CMMLCLIP and TIBVA in each label setting, demonstrating its effectiveness in leveraging in-labeled data to improve model performance. In the hateful memes dataset, SemiMemes achieves higher scores than HateClip-Per in all settings, albeit with smaller performance gaps. Notably, SemiMemes has significantly fewer parameters than HateClip-Per, which could be advantageous in real-world applications where computational efficiency is crucial. The results highlight the potential of SemiMemes as a competitive model for multimodal fusion tasks, particularly in scenarios where labeled data is scarce. By leveraging both labeled and unlabeled data, SemiMemes can achieve better performance than purely supervised models, showcasing its ability to effectively utilize all available information during training. The model's ability to harness the power of semi-supervised learning makes it a promising solution for real-world applications where data is often limited. Sentiment analysis of Internet memes is a crucial task, as harmful content can spread rapidly online. To address this issue, researchers have proposed a novel multimodal semi-supervised learning approach, SemiMemes, which combines the strengths of CROMAE and RAWNCOOK models to overcome annotation challenges. By leveraging the vast amount of unlabeled memes on the internet, SemiMemes achieves higher efficiency compared to existing methods. Experimental results, as demonstrated in Table 3, show that SemiMemes outperforms the state-of-the-art model, HateClip-Per, in identifying misogynistic and hateful memes in low-labeled data settings. Specifically, SemiMemes achieves higher AUROC scores on the dev scene and test scene sets of hateful memes, while requiring significantly fewer trainable parameters. The significance of SemiMemes lies in its ability to mitigate the time-consuming and labor-intensive annotation process. By utilizing in-labeled data, Semi-memes can conserve significant training resources while maintaining high performance. This approach has the potential to facilitate the development of more effective and efficient sentiment analysis models for Internet memes, ultimately contributing to a safer online environment. This page presents a comprehensive list of methodologies, concepts, and research findings in the field of computational neuroscience. The text delves into the intricacies of neural networks, their computational models, and how they are applied to understand brain function and behavior. The paper begins by introducing the concept of Hodgkin-Huxley models, which describe the behavior of neurons using differential equations. These models are crucial for understanding the electrical properties of neurons and how they generate action potentials. Next, the text explores the realm of Wilson-Cowan models, which focus on the interactions between different types of neurons within a network. This section highlights the importance of these models in understanding pattern formation and synchronization in neural networks. In addition to these traditional models, the paper also discusses more recent advancements in the field, such as the use of Hodgkin-Huxley models with detailed morphologies. These models take into account the complex geometry of neurons and provide a more accurate representation of neural activity. The paper also delves into the world of synaptic plasticity, a key mechanism underlying learning and memory. It discusses various models of synaptic plasticity, including Hebbian learning and spike timing dependent plasticity, which are essential for understanding how neural connections are modified based on experience. Furthermore, the paper touches upon the role of oscillations in neural systems, emphasizing their importance in information processing and communication between different brain regions. It highlights the various types of oscillations observed in the brain, such as alpha, beta, and theta waves, and discusses their potential functions. Finally, the paper concludes with a discussion on the limitations of current models and future directions for research. It emphasizes the need for further exploration of the complex interplay between different neural mechanisms and the development of more sophisticated computational models that can capture the full range of neural phenomena. Overall, this page provides a comprehensive overview of the key concepts, models, and methodologies in computational neuroscience, shedding light on our current understanding of the intricate workings of the brain. The authors present a comprehensive catalog of 26 instances of gravitational lensing events, each characterized by a unique set of observational features. These events are categorized into 3 distinct classes based on the morphology of the lensed images: 12 quadruply imaged quasars, 7 doubly imaged quasars, and 7 Einstein rays. The catalog is constructed by leveraging a novel algorithm that combines machine learning techniques with traditional astronomy methods to identify potential lensing events in large datasets. This approach enables the detection of subtle features that may be missed by human inspection alone. The authors apply a rigorous vetting process to validate the authenticity of each event, employing a range of diagnostic tests and simulations to rule out alternative explanations. This includes assessments of the lensed image morphology, spectroscopic analysis of the quasar and lensing galaxy, and astrometric measurements of the system's geometry. The resulting catalog provides a valuable resource for cosmological studies, offering insights into the distribution of dark matter and dark energy on small and large scales. Furthermore, the authors demonstrate the potential of this catalog for constraining models of gravity beyond general relativity, highlighting the significance of these events for advancing our understanding of the universe.